Okay, so I'm sorry that this isn't looking like WebAssign. Grabbed these I grabbed the opened up the at WebAssign and did this a couple of days ago and barely getting around to getting this video recorded. So these are the grades. There was 12 A's, 26 B's, 32 C's, and 30 D's. And then they're asking us to find, fill in that table, right? So uh, what happened was, I don't remember why. Here, just a minute. Yeah, I just opened up WebAssign, another preview, and the numbers have changed, so I can't. I was going to take a picture of it, but I know there's 100 here. Let me get a pointer going. So there's 100 people here. It tells us that up in the top, or 100 grades. It tells us up in the top. So I add how did I get to 12, but I added up those numbers and subtracted from 100. I got 12 left over. Then we're assuming that we're testing the claim that all multiple choice answers are not evenly distributed. Well, what if they are evenly distributed? That means it's 25% D's, 25% C's, 25% D's, and 25% A's. So I change those to a decimal. And then, of course, they have that missing, there's an empty blank here in WebAssign, and they're looking for 0.25. And then if there's 100 grades total, and they're evenly distributed, we'd expect 25 in each category. That one's empty, okay? And then we come up with that last column, and that takes a process to calculate. They're asking us to calculate that squared, what is it, sum of squared residuals. I don't remember what WebAssign calls it or what Dr. Stevens calls it. But you got to do this process of the observed value minus the expected value, and then square that difference, and then divide by the expected. And that's what WebAssign is looking here. That I would do that calculation. So I had 12. So for the first one, I had 12 observed. I had 25 that I expected. So I went 12 minus 25, which is negative 13, over the expected value of 25, right? So if I square negative 13, I get positive 169. And 169 divided by 25 is 6.76. And of course, you would have seen that on the table if we could look at this version of it. And then the same deal here. I had 26 expected, 26 observed, 25 expected. 25 minus 26 minus 25 is 1. I don't know where I wrote negative 1. Oh, that's funny. Well, the nice thing about it, if I square it, it's positive. So that should be a positive 1 there. And then divide by 25, we get that number. And then down here, we'll do 32 expected, 32 observed, 25 expected. Subtract them, we get 7. Square it, we get 49. Divided by 25, we get that. Then for my version of this, and I'm pretty sure it's the same for all of them, we're looking for this square right here. So 30 minus 25 is 5. Square 5, we get 25. 25 divided by 25 is 1. Now, is yours going to be 1? I don't know. Probably not. Then to get the chi-square number, to the bottom part of that table, you're going to add up all these squared residuals or squared errors, right? And that's the chi-square value. And then it asks for the number of degrees of freedom. Well, this is a one-way table. This is a goodness of fit. And so what you do is you take the number of categories, subtract 1, and that's 3. And then what you do is, just a minute here, I've got this on another table. I do have a picture of the table. So 3 degrees of freedom, WebAssign showing a 1% level of significance, 0.01. So that's going to be the critical value of chi-square. And that's what WebAssign's looking. And then do we reject HO? Well, let's see. I got to pull this down so I can see this. This is that whole rejection region idea. And if this were a normal curve, it would look like a normal curve. But this is the chi-square distribution, which is a different, it's a right skewed, right-tailed thing. So here's our rejection region, 11.35 or 45, and our test statistic is not out that far. It's not in the rejection region. So that means you're going to fail to reject HO. Remember, that's the rejection region. If your test statistic's out far enough away, we can say it's not due to chances of statistical significance, and that's not what has happened here, okay? So we're going to say there's not enough data, Dr. Stevens' phrasing, that there's not enough data to support the claim that correct answers for all multiple choice questions are not evenly distributed, okay? So that's when it's equal probability. I also did number two because that comes up. What happens when they aren't all the same? Okay, so this is another goodness to fit question. We're looking at colors of M&Ms, and instead of each color being equally distributed like the test questions, we're looking to see does the distribution of M&M colors follow this company's established um, distribution. They said 30% of them should be brown, 20% should be yellows, 20% should be reds, and 10% for each of the other colors. Okay, so the web assigned questions looking for the 66, and of course the way I did that, just like with the test questions, I found the sum of these and subtracted from 200 and got that. And then because these the established norms, that's going to be whatever it point to. Yours answer will be point two. And then to get the expected, well, if 20% of these M&Ms are supposed to be red, 20% of 200 is 40, and say 30% of 200 is 60, and 10% of 200 is 20. Okay, so that helps. Then to get uh, then the last column is that again that calculation. So for the goodness of fit test, we're going to do observed minus the expected. So 66 minus 60 is 6. I squared it. I got 36. I divided it by 60. That's the expected. I got 0.6, and then so on and so forth. 35 minus 40 is 25. I squared. Ooh, I wonder if I did this one right. I don't know why I wrote. I don't know why I wrote 25 there. I should be right. Oh, I see. Observed minus the expected. I don't know why you wrote that as negative. Like 35 minus 40 is negative. It should be 5, not negative 5. So I square that. I got 25. 25 over 40 is that decimal. And then 44 minus 40 is 4. Very strange. I did both of those as negative. And the other problem too. Anyways, so I got 4, squared it, divided by 40, got 0.4. Same deal, same deal, same deal. Okay, then you add them up. There's chi-square. And degrees of freedom is 5 in this case because there's 6 categories, and we're testing this at the let's see what level, at the 5% level of significance. So looking at the table, 5 degrees of freedom, 5% level, so 11.071, and I see when I wrote this down I was using, what did I do wrong? Maybe you can figure out what I did wrong, which really isn't a bad exercise figuring out where somebody went wrong. I wrote down that. What did I do wrong? I hope you realize I used the wrong level of significance. Or maybe my version, when I looked at this, had a 5% level. I had a 1% level. But right now, the one I'm looking at has a 5% level. So in that case, I would do that. Either case, though, regardless of the of the decision here. Let me delete that. That does not fall. That test statistic does not fall in the rejection region. So we're going to fail to reject HO. The data. What claim are we testing? Um, what's the claim? I didn't write that down. You suspect. It says I suspect the maker's claim is not true. Well, no, I can't. The data doesn't support that because that's not in the rejection region. That's perfectly within reasonable bounds to get that distribution if these are the true distributions. Okay, so that's a goodness of fit by hand, not hard. I encourage you to. I mean, you can certainly use. I've got a goodness of fit calculator you can use. Just grab screen captures of it. Um, and then the two-way tables, please go use that calculator that I have. It works really well. I've got videos about how to do that. Hopefully this helps you fill in the table.